Thank you so much, and thank you all for coming. Um, I'm just overwhelmed by this place and everything, but I'll do my best. So my plan, my sketch for these, so these lectures I was told are aimed at beginning PhD students. I'm not sure how many beginning PhD students there are. Yeah, you're right, Kelly. Are there really any? I mean, seriously, it would help me to know if there are PhD students, and if so, how many years into your PhD you might be? Two? Okay. So as the first year, wonderful. Thank you, thank you. And you should definitely interrupt me if anything's not clear. And these are going to be extremely informal. So my plan for the 4 lectures is one will be on causality, so Lorentzian spacetime. I hope this is readable. And causality. The second will be on geodesics, focusing, and a key equation that's called the Raychaudhuri equation. The third one is to be on, and Hawking. This is all part of one thing, Hawking Singularity Theorem. Then the third lecture will be on null geodesics, which will take us quite a long time because this is a significantly more difficult subject in my opinion. And then let's see, yeah, and then here we have Penrose's Singularity Theorem. And then the fourth lecture most likely will be whatever I couldn't do in lectures 1 to 3, but if there is actually some time, I'll say a little bit about black holes. So a quick word about the philosophy of these lectures. So I sort of chose these topics to lecture on, and they're all really seriously prehistoric. These developments start in the 1950s essentially, and go on and sort of end by 1970. So, why am I talking? And so in these lectures, there will be no ADS, no CFT, no de Sitter, no entanglement, no quantum, no anything that's modern research. So why am I doing this? And the real answer is I have no idea. It's just what I can do. But I think if I have to post facto justify it, I think all the modern developments are built on some understanding of this. And my experience is that these things are generally done in a hurry, with a collection of statements that you're supposed to buy, and then I think this is how, I know this is how, at least where in India, for example, PhD students often get trained. I think it's quite universal that you pick up a few buzzwords from all this stuff and then you jump to, I don't know, Busso's entropy bound or whatever modern thing you want to do. So maybe if you spend these few hours here, it'll become clearer what all these are, what was the thinking, why this happened, and then you can still do Busso's entropy bound, which I'm sure is more or anything like that, ADS, CFT, islands, or whatever the current things are, and I just hope this will form some basis to understand these things. So with that out of the way, let's start. And I think the first thing that I like to explain to beginning PhD students is the important difference between space and space-time, just belaboring the obvious, but we are going to do a little comparison here. So this is space and this is space-time. And it's very, At least for me, it's very easy to be confused when I see a diagram. So in this diagram, I have x, y, and z. And in this diagram, I have x, y, and t. And there's also a z, but there's no space to draw it. And so just to state a few obvious things before we start giving you definitions and stating theorems, this is a point, and that's all it is. But of course, this isn't a point, this is an event. So to find out what point it is, I project it down and I find its x and y coordinates. To find out at what time it happened, I project it this way and I find its time coordinate. And this is the source of endless confusion because we often draw paths, and if we have a path from one point to another, this path is just a path between two places in space. And if I do the same thing here, I'm really drawing a path from one point in space at one time to another point in space at a possibly different time. There's not that much you can say about this path. It can have any shape. It could be from P to Q there, or it could go this way, or it could go that way. But as it turns out, in space-time, there's a very, very fundamental difference between paths that look like that, paths that look like that, and paths that look like that. They're completely different. These are called time-like. We'll make all these definitions formal in a minute. These are called null, and these are called space-like. And everything possible, well, you have to bear with the quality of my drawing. That's the null one. Now here it's just Minkowski spacetime. We'll obviously have to consider more complicated spacetimes, but no, this is terrible, isn't it? Okay, we get rid of the y-axis, which was just confusing everyone. Here's null, here's time-like, and here's space-like. So I'll write down the definition in a second. Now, one thing that's very valuable to keep in mind at all times is that a physical object can only undergo a path that's time-like or null, but it cannot go space-like because that violates causality. So this path that's space-like is moving in x a distance faster than light can move in the given amount of time. That's why it's called space-like. And so this is not physical as a path to be actually taken by some physical object. Okay, now we can compare paths. So if this origin is now and here in this room, and I do literally nothing, then I travel this path. This is me 5 minutes later. This is me 10 minutes later. This is me after I've been thrown out of the Royal Institution because I didn't give a lecture on anything useful. So this is a sort of kind of path that just happens. And okay, or this is me at rest. This is me on a British train. This is me on a French train. This is me on a Chinese train. So you see, these are all ways of thinking about space-time diagrams. And it's very important because there just is no analog here. There's literally nothing nicer about this path versus that one. Okay, and that's because this has rotational invariance. What this has is Lorentz invariance. So of course I can go from any of these paths to another by boosting, but that boosting is not something that humans are mentally equipped to do when looking at a picture. So that's why these pictures, there's no natural transformation we can make while staring at the board, which takes us from that to that. While if I want to go from this to this in space, I just tilt my head and I'm done. So this is very important to keep in mind. And of course, we are going to be interested in those sorts of diagrams. So with that sort of very vague set of comments, let's start defining a few things. So what's the space-time? This is obviously the first thing we need. So spacetime is a differentiable manifold. The works of Hawking, Ellis, and the book of Hawking, Ellis, Wald, etc. are full of words like C infinity, which means infinitely differentiable. I'll try not to be so formal. So with a smooth pseudo-Riemannian metric. Do you think I can move this table a bit, because I think I'm blocking this board as I write? Oops. Yeah. Thank you. This is much better. Pseudo-Riemannian metric. So Riemannian metric is one where the distance is positive and it has to obey triangle inequalities and so on. And pseudo-Riemannian is the typical example is a Minkowski metric where there's one negative sign. So for example, this. And then it doesn't obey any of the standard properties of a metric because it could be negative due to this, it could be positive, it could also be zero. And the triangle inequality in its standard form doesn't hold, things like that. So this is basically the definition. But there's also one more little thing, which is that it's time orientable. It's very intuitive. If there's a sense of, so if, what's the exact statement? A notion of future and past. If there exists a notion of future and past, and that's preserved by coordinate transformations. So obviously a manifold, a set of coordinates, so we'll denote the coordinates by x mu. Mu goes over 0, 1 up to d, and x0 time should have, so there should be a sense that time positive points to the future, time negative points to the past, and if that can be continued successfully all over the manifold, then I have a time orientable manifold. So that's a good thing to have, because again I emphasize there's really no serious analog with a space diagram, because positive x and negative x are completely up to me. And it's important that there's only one time. If there were two times, this would become more tricky, because I could continuously rotate from something pointing in the future to the past. But because there's only one, at least for most physicists, this is well defined. Okay, so now let's consider paths. So a path, for me a path is the same as a curve. And I'll tell you its characteristics, or let me tell you right now. It's always going to be continuous, and usually, but not always, smooth. So continuous simply means there are no breaks like that, so everything joins up. And smooth means there are no kinks. So this is not smooth if there's a kink at this point. And you can allow it, but then you have to be sure you know which ones you're talking about for which theorem to hold. It will turn out that geodesics don't have this kind of kinks, but a path in general could have one. And we'll parameterize it as x mu of a parameter lambda. And then we'll call it time-like if this thing is negative. We'll call it space-like if it's positive. And we'll call it null if the same thing is 0. And since my paths can be non-smooth, they might choose to be one of these in some segment and one of these in some other segment. Even if they are smooth, they can actually choose They can vary across all of them. So for example, if this is x and t, my path could very well look like that, in which case it's time-like here. And then when it reaches exactly 45 degrees there, it becomes null for a little while. Then it becomes space-like. I'll use TL and SL for time-like and space-like. And then after it curves over here, it's again time-like. So I can certainly have a path that has time-like, space-like, and null segments to it. Of course, whenever you transition between time-like and space-like, you'll always go through a null region, and vice versa. When you go back from space-like to time-like, that's also null. So null is always at 45 degrees. Good. Okay. Now let's start using some words that the serious people use. So, and there'll be quite a few definitions. After a couple of them, I will pause for questions, but you can always interrupt me if you like. The chronological future of a point. So a point P will always be a space-time point, so it's what I called an event earlier. And so the chronological future will be called I plus of P. And for everything that's a future, there's also a counterpart that can be called the chronological past. And so that will be I minus of P. So I'll usually define only the future one, and then the past one is obtained by flipping the direction of time. And it's the set of points in the future. Remember, my manifold had a well-defined future direction, reachable from P by a time-like path. Okay, so to illustrate this, yes, I have a whole other board, but somehow okay. Is it difficult for you, or it's just okay? I probably just keep using these three. By a time-like path, and so in Minkowski space, so I warn you, the only, most of the time the only illustrations we know how to draw are in Minkowski space. It does not mean it's the most general, it's nowhere near the most general. If it was, there wouldn't be any of these lectures in the first place, but let's understand it in that case anyway. So here's my point P, and I plus is here, is this shaded region, and now it starts to become important. Does this include the boundary or not? So the answer is that it does not include the boundary. Because when I said reachable from P by a time-like path, I meant the path is everywhere time-like, and there's no way for me to be everywhere time-like and end up at a point here starting from P. The only way I can end up at this point starting from P is to either go everywhere null along the light cone, or to go here and then turn space-like, but that's really bad. That's something I'm never allowed. So I plus of P is that shaded region, I minus by time reversal is just the one in the back. And it's good to give a name to these boundaries. So this boundary goes by the name del I plus of P. It's actually the union of that and this, and I guess it's clear that we really mean a cone of revolution around the vertical thing. Now this is one standard notation. Here's another one which I never could understand why, but Hawking, I think, and Wald, I think, both like I dot. It's the same. It's just notation. It's either called del I plus or it's called I dot plus. So it's the boundary of I plus. Okay, so that's the chronological future, and this was important. Strictly time-like, there's no null in this, There's no space-like in this. It's all strictly time-like. Good. And now something that is an obvious generalization but has different properties is the causal future, and it's exactly the same definition except that reachable by what? So in the future, again, causal future is reachable, set of points in the future reachable by a causal path. And causal path means time-like or null. So it can be everywhere time-like or everywhere null, or it can be sometimes time-like and sometimes null. And since I said we have not insisted on smooth paths so far, it can have segments which are time-like and segments which are null. Okay, so chronological and causal differ by the fact that chronological means time-like only and causal means time-like or null. And this is called J plus of P. And there's obviously a J minus of P that goes with it. Okay, are there any questions up to this point? Please do feel free. I think it's very, very simple. It will get complicated maybe in a little while, but for now this is it. Okay, now I define the future of a point or the past of a point, either chronological or causal, but I can quite easily generalize this to S, where S is a set of points, and it's trivially the same definition, and I plus of the set S is simply the union over all points in that set of I plus of the point. Okay, and pictorially what you can do is to just change this diagram a bit. Let this be S. So this segment could be a disk, or it could be a ball, or it could be pretty much anything you like. And whatever it is, every point in it is going to have its own causal, chronological or causal future. And so in this case, the interior of the shaded region is I plus of S. And the boundary will be del of I plus of S or I dot of, yeah. Okay, good, fine. There's a set of notes I have which I'll be happy to make available. It has exercises to illustrate all of these points. Now we can get to something a little more interesting, which is the causal diamond. After this, I'll pause and slightly try to tell you physically what we're trying to achieve by doing all this. It's a lot of formalism, and I don't want it to look completely dry and boring, so but it's needed. So let's just do it, and then let's ask what it's good for. So here's a point P, and I assume there's a point Q in the future of P. Now I'm not saying what kind of future, just in the future. So remember, future, there's a time, and so if there's some coordinates, there's some time, and there's a notion of future built into that time, and if this time is later than this time, then it's in the future. That's all I've said. And now what I can do is to consider the causal future of P. So let's put Q here for now. So the causal future of P is that shaded region. So that's J plus of P. And the causal past of Q, this is J minus of Q. And if I intersect these two regions, then I get a diamond. And so the causal diamond dpq is J plus of P intersected with J minus of Q. I'm not sure if this goes behind your horizon somehow, but okay. Anyway, so that's the causal diamond dpq. Now, it's easy for dpq to be empty. For example, I have a point like this, that is J plus of it, and I just pick Q here, which is quite space-like with respect to P, and this is its J minus of Q, and very visibly they fail to intersect, and therefore dpq is just empty. So this can happen. Okay. Now, so far we haven't said a word about geodesics, and now I think we'll state our first theorem, which does involve geodesics, and it's also the first theorem that involves proving something that's quite non-trivial. So this is the statement about something called a convex normal neighborhood, and let's define it. Okay, before I get on to this, so I promised a little statement about where we were going with all this. So the goal of the physics material I'm discussing is to understand the nature of spacetimes that are not certainly not trivial like Minkowski spacetime. They could be non-trivial solutions to Einstein's equations. They could even be non-solutions to Einstein's equations, but most often we'll work with solutions. And we want to understand a very key property of these spacetimes, which is, do they have something wrong with them? Which colloquially goes by the name of singularities. So do they have singularities? As we'll see in a fair amount of detail, a singularity is not as bad a thing as you might imagine from hearing the word singularity. The word singularity nowadays has been replaced by geodesic incompleteness, which is a much more mathematically correct statement. Singularity sounds more sexy. It's the one that's used in newspapers, but it's not very precise. But in any case, it's bad, and geodesic incompleteness is bad also. We'll be defining both of these. And we want to understand whether generic spacetimes have these or don't have these, and if they do, then under what conditions do they have these kind of bad things happening. Now, in order to prove something as serious as that my spacetime has an awful place in it, a point where something breaks down, maybe a point where curvature diverges, or a region where something goes wrong, in order to prove any of those things, I need fairly rigorous mathematical theorems, and I need to be very clear in my mind whether the spaces and the subspaces I'm talking about have boundaries, don't have boundaries, if they are they closed and bounded, then they're compact. So notions of compactness, for example, which normally a physicist could care less about, to be frank, but here they really sort of dominate, because ultimately Penrose's singularity theorem really uses compactness and closedness in a very non-trivial way. And so we need everything to be extremely well defined before that. And well, this is a sort of one-line explanation why Wald's book is what it is. It's heavy duty stuff, especially from chapter 6 or 7 when all this sets in. Or Hawking and Ellis, which is heavy duty from page 1 for some reason. It's a much more impenetrable book for the beginner, but contains much of the same material, and in fact much earlier. I would say the chronology is Hawking and Penrose's work is 60s till early 70s. Then after that we got more modern stuff like black hole thermodynamics. Then there's Wald's book, which I think dates from maybe the late 70s or something, maybe 80s, I'm not sure. And then most recently, and for me in a way, brought a fresh perspective, was Ed Witten's lecture notes. I've circulated these references from a few years ago, and I had the fortune to attend his course in Princeton University about 2 years ago. And he brought a certain more geometric perspective to some of these ideas, which I'll be talking about in later lectures. Okay, so I hope that collection of comments sort of, there's a kind of trade-off. As physicists, we want to do things as crudely, roughly, and get to an answer as possible, because we are not mathematicians, at least I'm not, and all these people are not, in fact. and yet we are not going to get any sort of sensible theorem unless we insist that, you know, something be compact and we can prove it, or something be closed and we can prove it. So those proofs are really important, and so formalism is important. Okay, any questions? Really, please interrupt. I would love to be interrupted, then I would know what, you know, whether this is all too easy, too difficult. Yes, please.
Yes, so I was a bit confused. You introduced I and J.
Hmm.
So what is
Yeah, so I is chronological future, and thank you. I'll summarize it here. So there's just one word of difference. So I plus is chronological future, and the meaning of that is reachable by a time-like path, and J is causal future, and it's reachable by time-like or null path. And so here we are distinguishing whether a person traveling by a massive object, or a person traveling by a train or plane or rocket ship or something else can reach that point in the future, while here we are also allowing it to be a beam of light that can reach that point in the future, that event in the future. So if you allow null points, then you get a larger space called J plus. In Minkowski spacetime, I plus is simply the interior, and J plus is I plus as well as this boundary. But it would be fallacious to think that J plus is always I plus along with its boundary. That's actually not true in general. And there's a famous counterexample which I'll give you since you asked. So let me imagine that I delete a point on the light cone, just one point on the light cone of P in its future. I just delete it from my manifold. Once I've done that, what's I plus and what's J plus? Well, I plus could care less because this point was deleted from the light cone, which was never in I plus, so I plus is still the same. So I plus is the same. Now as for J plus, it's missing something because J plus did include the whole light cone, and it still includes this segment, for example, of the light cone. Now imagine this to be a cone, and I've just deleted one point, but any straight line that would have gone through this point and reached here, this later part of the light cone, is not in J plus anymore, because there's no way to access this point from here by a null path. Certainly I can't access it by a time-like path, because once I'm in, I never come back. That's just a property of being inside the chronological future. You might think that since this is a cone, I could go at some angle in the cone and then curve around, but you can't be curving around on the light cone and keep going at the speed of light. To go at the speed of light, you need to go radially along the light cone. So these points are not in J plus, they are also not in I plus, however they are in the boundary of I plus. And that's because I plus is everything except that, but the boundary is what it approaches arbitrarily close to, and so the boundary of I plus is, it does include, it doesn't of course include this point because this point has been deleted, so it's just not in anything, it's not in my manifold at all, but all such points beyond this are still in the boundary of I plus. So I plus and J plus are not equal, and in general J plus is not the boundary of I plus. I hope that example was illustrative. And actually, let me say that mathematicians as well, I mean, and also Hawking, Penrose, Witten, and so on, Wald, almost always will prove this kind of non-triviality of these statements by deleting one point, which is extremely annoying in a way, because you're like, why as physicists should we be deleting a point from space-time? It's just not something a normal human being does. But you know, it's important because it shows that these definitions are non-trivial. And then if the manifold was, this is Minkowski, right? It's not, it is trivial. You make it non-trivial by deleting a point. But if it were a black hole space-time, it's already non-trivial and it's already very difficult. So it's good to know these things before we get to those examples. So that's the purpose of these weird mathematician-like examples. Good. So convex normal neighborhood. So now we invoke geodesics for the first time. So I'll call this a CNN for short, convex normal neighborhood. And the point is that I have a manifold. And let's say I have 2 points in it, Q and R. No, first let's say I have a point. Okay, good. Let's say I have 2 points Q and R. And the question we'll ask is there a unique geodesic between them? So a few words about geodesics. Geodesics are curves that extremize the distance. And distance in the Riemannian case just means distance, but in the pseudo-Riemannian case, it could mean any of these 3 kinds of invariant distance, the space-like, which is the invariant distance, or the time-like, which is the proper time, or it could be null, in which case actually there's nothing to extremize because it's just 0. But this is the usual statement. And the way they are defined is to say that they are curves x mu of lambda such that dx mu by d lambda is, so I differentiate dx mu by d lambda, which is the tangent vector to the curve manifestly. I differentiate it along the curve, and my answer should come out proportional to the original tangent vector. So what I'm doing in that case is taking a curve, and at one point I have a tangent. Now I translate to another point where the tangent remains parallel to what it was, and by doing this repeatedly I construct the curve. And what I'll get by doing this in a trivial space-time like Minkowski or Euclidean is just a straight line. But if the geometry is non-trivial, I won't get a straight line. Okay, so let's unpack this equation a little bit. This is nothing but so let's give a name to dx by d lambda. This thing we'll call t mu. Then d lambda is just t kappa d kappa of t mu. This is x t mu. So this is the geodesic equation in general, not x alpha. Okay, now everything should be clear. D kappa is the usual covariant derivative in space-time. So it's d by dx plus an affine connection term. And I project it back onto t, and it should be proportional again to t. So the directional derivative in the covariant sense of the tangent vector is again proportional to the tangent vector. That's the geodesic. And this definition holds in the Euclidean case where kappa and mu run over say 1, 2, 3, but it also holds in the Lorentzian-signature case where they run over 0 up to d. So that's the geodesic. Now lambda is just a parameter which parameterizes points. So it's a curve x mu of lambda, and lambda sort of increases or decreases as you go along this. So that's what lambda is. It's just a number. Okay. Now there's a theorem that it's always possible. Okay, now the theorem is important. It's important to distinguish. So first we get to the first we do this for space, and then we go to space-time. So in Euclidean signature, it's always possible to send lambda to lambda prime of lambda such that alpha is 0. In other words, make the right side of this equation 0. Okay, let's first unpack this equation. So this equation in detail for x, this equation is d2 x mu by d lambda squared plus gamma, the affine connection, mu nu lambda dx mu by d lambda x mu by d lambda equal to alpha mu by d lambda. Okay, this equation is just that, and right, because the first term is ordinary d by dk, but dk is the projection of the ordinary derivative along the geodesic, so it's d by d lambda, and then the next term has a covariant derivative and it clearly becomes that. And it's always possible to get rid of this, and if we get rid of this, then this whole combination is called 0, and in this case lambda is called the affine parameter. So we can parameterize a geodesic how we like, but the good parameterization, which makes the equation simpler, is by the affine parameter. That's a lesson we learn. And a nice thing is, once I have one affine parameter, then any other affine parameter related only by scaling and a shift is also affine. So the entire family of affine parameters is found if we know one of them. And another very nice feature is that we always know one of them, because we can use the proper distance so g mu nu dx mu dx nu, let's call this d lambda as the affine parameter. And what this means geometrically is that as I go along the geodesic, I trace a small interval along a geodesic. I say, well, the amount of parameter I've shifted by is the proper distance between those two nearby points on the geodesic. Okay, the theorem, which I'm not proving here, is that if we choose lambda to be given by this invariant expression, then lambda will be affine and alpha will be 0. That's something you can actually prove. So that means there's a good affine parameter in our problem, which is the invariant distance. And there are other equally good ones, which are the scaled distance or the distance with an origin shifted. Now, if you have a distance, you can always shift its origin. So that's what B is doing. So it's obviously not something very complicated. And A, yes. Square root. Sorry. Yes, exactly. Sorry. Good. And so, and scaling, of course, is again no big deal. It just means I uniformly increase the rate at which I'm traveling, or the distances I'm measuring. There's no scale of distance, so I can as well scale them. Okay, there's nothing else. So this is in the Euclidean signature case. It's not so simple in Lorentzian signature. Sorry, I claimed I was going to discuss the causal convex normal neighborhood, but I digressed because I realized that I had first to discuss geodesics, and then I can tell you what's a CNN. So I'm on geodesics now. You must tell me if this is all trivial stuff. Is it stuff that you like already know? It's not, especially the first row, please, because that will determine how much faster or slower I should go. Yes, no, faster, slower? You're okay. Okay, good. All right, now with Lorentzian, we have some fun. We'd like to do, so everything up to here is the same. In fact, I've used Lorentzian notation. Really, if I was talking of Euclidean signature, these Greek indices should have been Latin. I think you can understand that. It's just the same equations. But this proper distance starts to be problematic. So the proper distance, first of all, can be root g mu nu dx mu dx nu. Remember, we said this is positive for space-like distances, and so yes, if we have a space-like distance, we can use this as, and it is an affine parameter. If we have a time-like distance, we can also use this, but with a minus sign, because then this number is negative to start with. And so there's a minus sign, and then under the square root, now that's positive, and we can use this as the affine parameter. This is very good. Unfortunately, when it comes to null distances, this square root is equal to 0, and 0 is no good as an affine parameter. And this is one of these situations. I must say that in the first course on GR, you don't quite appreciate the true horror of null distance, null directions. It's really awful. I mean, it's just full of things that are completely counterintuitive. And here's just the very first one. They just refuse to obey normal rules. I'll show you many more examples. So here you have to choose an affine parameter arbitrarily. So you have to be clever enough to find one. The good news is that once you found it, and if someone else you know has found another one, they'll be related by this linear scaling plus constant shift. So at least there aren't that many available, but you cannot deduce it just by knowing these invariant distances, because, well, they're all 0, so it's no good as a parameter. So it's not that there isn't an affine parameter, it just has no relation to any invariant quantity. Okay, so this is a new feature of the Lorentzian case. And I think that's what I needed to say about geodesics, and now I can tell you the CNN theorem, which says the following. Supposing this is my manifold, and I have a point Q and a point R, then I should have at least one geodesic between Q and R. And of course, whether it is time-like, space-like or null would depend on Q and R, which I'm not specifying for now. But the question is there a unique geodesic from Q to R? And I think in
the first claim is that for any 2 points I select in the pseudo-Riemann manifold, regardless of the choice of method, there exists geodesic.
A geodesic, yes. I think this is just connectedness, because a geodesic will make the, as we started by saying, okay, maybe I forgot to say one more thing. We started by saying geodesics are obtained by parallelly transporting the tangent vector, but they also extremize the invariant distance, whatever that might be. It might be a space-like distance or a time-like proper time, or it might be null, but they always extremize it. And they may have arbitrary, we'll come to the possible lengths they can have. That's very important. Right now, we are not so worried about their length. We're just worried about whether there's more than one geodesic between Q and R. And let me give you the intuition for this question. Your manifold might be sufficiently strange that starting at Q, I go somewhere else and come back to R. Having gone, so to say, around somewhere to the back of the manifold where there's some region where my distances are very compressed for whatever reason, because, right, it's an arbitrary manifold. And how do I know that this isn't also going to be a geodesic like that one? And in general, actually, I don't know, and in fact, there can be many geodesics between points Q and R. I literally do not know. The convex normal neighborhood, however, is a theorem which is very useful, which says that given a point P, there is an open set of the manifold. This is the whole, this square is the whole manifold. This is an open set that I call U. So given P in M, there exists an open set U in M. So open set, of course, means it's open in the topology on M, which I assume is given, such that there is always a unique geodesic between every pair of points. So the intuition is the manifold might be large, it might have all kinds of magic going on somewhere far away from Q and from Q, for example, but there's a neighborhood around any given point such that any pair of points inside this U has a unique geodesic. So this mischief of having another geodesic is sort of blocked off by U being small enough. Right? So if there wanted to be another geodesic, it would have to go outside U and come back, and we can ignore it if we are working entirely in U. So this is the existence of a convex normal neighborhood. It's interesting. Sorry? Yes, of course. No. I don't say. I start with P in M. Now there exists a U in M, of course, containing P. Yes, that I agree. Okay, sorry. The correct statement is there exists a neighborhood, an open neighborhood U of P in M. Yes, thank you. The idea is that we don't do this by fixing a pair of points and asking the question. We fix one point and then we ask the question for all pairs of points which are reasonably close in the topological sense to P. Okay, so all Q and R, between every pair of points Q and R, there's a unique geodesic.
Definition of topology in Lorentzian-signature. So if it is Euclidean-signature, it's only to just metric space, it's topology.
Thank you.
So in this case,
yeah, that's a very interesting question. So the point is that the metric, of course, we don't have to rely on a metric to define a topology, but it's natural to rely on a metric. And what, as I understand, even in Lorentzian signature, we rely on a Euclidean signature metric to give us the topology. So because yes, and in fact the works of Garrosh particularly have this, and Witten also, and maybe Wald also, have this beautiful thing that they're mired deep in some theorem that they're trying to prove, and they're like, let's introduce a Euclidean signature metric on this part of the space and prove something, and then you're like, sorry, what? But in fact, as you said, there are two metrics actually always in one's mind. So one metric is the given Lorentzian metric on my manifold. The other is essentially any Euclidean metric that I choose to use to define the overall space from the beginning, and it just helps me talk about open sets. It defines my open sets and I stick with that definition. Of course, there are famously all kinds of non-standard topologies on any set of points. There are non-standard differentiable structures on a given topology, and we are assuming here that we are always working with what you just said, the metric topology for a suitable Euclidean signature metric that satisfies all the Euclidean axioms, and then the standard differentiable structure also.
So now when you have this situation, can you reform the limit without referring to the metric at all?
No, I think not, because a geodesic is intrinsically a metric concept.
Yes, that's true.
Yeah.
If you're using topological concepts, purely topological concepts, which you'd like to describe in terms of a second, you pull it out of your back pocket.
Okay.
It sounds like the metric is not really essential.
Yeah, so the point is that the topology is essential, and there should be a topology on my space M before I ever put my Lorentzian metric. So the question is really, I never went into that. What did we do before introducing a Lorentzian metric to have a topology in the first place? And it's at that point where any sort of sensible Euclidean metric will do, just to define the concept of open sets. So the intuitive idea of an open set is a ball around a point which doesn't contain its boundary. Okay, that's the the rough idea of a metric topology. It's just the set of open balls.
So now consider magic that you allow yourself to do this game with deleting points or putting counters.
Yeah.
There's indeed a unique geodesic connecting to. Is it the case that this theorem theorem breaks down?
Yeah, so no, the theorem won't break down because this theorem is always true, and what I'll do is I'll pick a point and there'll be a u, presumably, which manages to leave out that ugly point which I've deleted. So if I have a manifold with a deleted point, that deleted point, as long as it's not the same point as P, I'm fine, because then I can always find an so this is separability. Now we get into this Hausdorff business, which is that, you know, given any point, I can enclose it in an open set which doesn't overlap with you or your open set. There are many levels of separability, but simplest one is that. So given that, I can avoid any point that I don't like and have this be true in the region. The important thing is, obviously, it's therefore not true on the whole manifold. We gave up saying that it's true on the manifold. We'll even see cases where it's just not true. But we lean on the fact that this exists for any manifold. Now, there's something I forgot to say. So, first of all, this is a theorem in ordinary differential geometry, not necessarily Lorentzian. So the proof of this theorem in ordinary geometry is found in the textbook of Hicks or any other textbook on differential geometry. But then when it's extended to the Lorentzian signature, then actually something else happens. There's a second part to the theorem. So part 1 is true in any geometry. Part 2 is for Lorentzian. So if we restrict J plus of P to J plus of P intersection U, this open set, then this region can be reached from P by a unique time-like or null geodesic. So obviously this part of the theorem doesn't even make sense if we were not in Lorentzian signature, but once we are, then what we do is we take this P and we draw its causal future, that's J plus. And now for topological reasons, I found a U, but once I found this open set U, I can simply intersect it with J plus and I'm here. And now this second part of the theorem, which is actually due to Hawking and Ellis, or Hawking maybe, but it's in the textbook of Hawking and Ellis, is that you can reach any point in this intersection region, which is bounded by this, this, and that from P by a unique time-like or null geodesic. Now we've brought in the kind of geodesic which wasn't there in the previous statement.
So,
yes.
I mean, this is the theorem that you're talking
Yes.
about.
Yes.
When you say, you probably find some way of insulting it, but the far side of the causal horizon you care, where you develop these closed time-like curves.
Yeah, I think, so I will come to closed time-like curves and globally hyperbolic spacetimes, but no, the point is that there exists a U, and what I can do, you see, if I have a closed time-like curve, it has to go somewhere and come back. If I stay within, so let's say I have a closed time-like curve from here back to here. The easiest way is to just make time a circle. So it goes there and it miraculously comes back here. It's closed. But but this is my original point, and I insist on working here. Now there's no closed time like curve. I shouldn't put a square. I should put this and call it U. So now my statement is that from my point P to anything inside U, I can go without by a unique geodesic, and of course that geodesic will not be causal unless I first check that where I want to go is in the causal future of P. So that's the second part of the theorem. Says if I want to go only somewhere in the causal future of P, then I can get there by a unique geodesic, which if this is time-like from here, it will be a time-like geodesic, and if the future point is not on the null In the null future, then I can go by a null geodesic, but unique. So the theorem really, it doesn't say almost anything about the global structure of manifolds. It says that you stay close to P, then you can do everything as normal people do it. And it's only if you stray sufficiently far away in a topological sense, then all hell can break loose and these things can happen. So one relies on the existence of this later on for certain things to be proved, that's all. It's not a grand statement about life in some sense. It's only about a very small region. Yes.
Is the theorem only useful for a Lorentzian manifold?
Yeah, no. So the first part of the theorem doesn't have any reference to Lorentzian geometry, and it is true in general. And in fact, originally it's a theorem in ordinary geometry, Riemannian geometry.
Like we consider like the Penrose code in the software.
Yes.
I think they're relative.
Yes, yes. But the theorem says there exists a neighborhood U of P. So if I consider your sphere, then this is your sphere, and this is your north pole and south pole. What worries you is that there are many geodesics from the north to the south pole. That's true. But this is my point P. Then there is a neighborhood of P in which there are not many geodesics from P to any given point. There's only one geodesic from P to any given point. It's basically that. So I repeat, it's not about the whole space, it's about the existence of a open set in the space where this is true. Yes.
Maybe it's a bit because it's about global structure. So how do you extend the definition of geodesicity to boundaries? So you go along with the bulk geodesic and then the boundary geodesic, and then if you want to be bulk geodesic, it's question.
Yeah, I mean, you can, I think. I think for most of my discussion, I think we will not just have boundaries, but I think we can do it with boundaries, yes.
Yeah, and then there's a question, all points are reachable by geodesics in such modularized sense if we start from infinite. So
Yeah, but
we lose uniqueness
yes.
without boundaries. But the question is there such situation that we cannot reach something if, for example, we have some cut out parts.
I think there's always a geodesic, right? Even if I cut out a block of my space or space-time, I can, as long as it's connected, it means by definition there's a path from here to there, to anywhere. That's connectedness. Path exists now, I just have to, so in Euclidean geometry, I minimize that path. Whatever I might get by minimizing it is the answer. Unless it's bottomless, but it can't be because the minimum in Euclidean is 0. In Lorentzian, it's more complicated, and I'll be discussing that.
He's saying nothing about whether the path has infinite length.
Right now, no. I'm not even worrying about the length of the path. We'll talk about the length of paths very soon, very soon. But I think we should take a break now. And then because the next part of this lecture is about globally hyperbolic spacetimes, which is a new wrinkle and very important one, but I think this is a good place to stop for a break. Okay, shall I start? Great. Okay, thank you. So, in the first half of today's lecture, so in the last hour and a bit, we talked about Lorentzian spacetimes and laid down some general rules, but without too much concern about whether physics could be done on those spacetimes. We did, of course, expect to respect causality because that's like a very, very basic minimum thing you need to do any sort of physics. But beyond causality, we didn't really talk about, whether you would be able to have an initial value problem, whether you'd be able to formulate your physics problem on a generic spacetime. And after many years of research by different people with different kinds of motivations, it emerged that the good spacetimes on which we should try to do physics are called globally hyperbolic. And to motivate this, we'll first give you a few definitions and then in fact, there are 3 definitions of globally hyperbolic, all equivalent, but they're all very different, but they can all be used to imply each other. So we'll get into that. One of the three is like very nice and very intuitive, so I'll mostly use that one. But before we get there, we have to define an acronal set. And this is really a key definition which will keep cropping up all the way till the very end of my last lecture. And so a subset, so M is always my spacetime, S is some subset, is acronal if for all P and Q, all points P and Q in that subset, the future, the chronological future of P does not intersect the chronological past of Q. So this is the formal definition. What does it actually mean? Basically, it means that in this S, in this acronal set, no pair of points can be connected by a time-like curve. So chronal we used for time-like, chronological future we used for time-like future, and acronal is that you can never join anything to anything in your set by a time-like curve. Examples, they're very simple examples. So for example, one example would be Minkowski space. So the xy plane is acronal because, right, I'm in this plane at a fixed time t, any fixed time. I want to get from one point to another in this set, and of course, so the time-like curve in that set. So I want to get from a point in this plane to another point in this plane. Well, I obviously cannot do that by a time-like curve. So that's one example of acronal. Now there's a subtlety, which is whether does acronal allow for null curves. The null is always, I told you, the nasty one, so you have to always think that through separately. So some authors, so different authors say different things, but actually in this case, I think null curve is still okay. So for example, the light cone itself of a point is also acronal because you're never going to get from this point to this point on the light cone by a time-like curve. Okay, if it's time-like, it takes off from here in a direction that's not exactly aligned with the boundary, and there's no hope that it'll ever get back here because it'll have to turn space-like. It'll be going slower than light, and to catch up with light, it'll have to go faster than light at the end, and it cannot do that, and so that subset is acronal. Now in both of these examples, I chose a set which is locally everywhere space-like in the first case, and this is locally everywhere null. And you think that's what acronal means, that my subset S is just space-like or null everywhere. And it should be, because if it wasn't, then it wouldn't be acronal, but it's not sufficient. This is a necessary condition, but it's not sufficient. So let me state that. Being everywhere space-like or null is necessary but not sufficient to be acronal. And for this, there's a standard example which tells you why. And in this example, I can just take M to be Minkowski as always, and my set S is a line which is wound like this. So this is my subset S. Remember, I never said that S has to be of any particular codimension or anything. So a line is as a good subset. And as you can see, so it's basically going in circles in this plane, but every circle it goes slightly up. So it's a helix. But this is the time direction. Now, locally, this is always space-like. I've drawn it in such a way that even though it might look like anything, but if you actually imagine it, there's no way where the tangent to this curve ever becomes null or time-like. It's just a very gradually rising helix. So it's everywhere space-like. You agree to that? So it's everywhere space-like. Why is it not acronal? Because, well, I'm here and I can just go here. So I've joined a point P to a point Q by a time-like curve. So actually, this was wrong. Actually, this also shows by a time-like curve in M. So it's acronal if there's no curve anywhere in the manifold which joins 2 points of it. So this example, I hope, clearly illustrates that point, that it is space-like everywhere, but that's not sufficient. This is not acronal. Because of the existence of lines like that. Good. Okay. And relating to this, there's a nice theorem which I'll copy and write down. For any set S in M, the boundary delta I plus of S. So what do? I take my set, this is S, this is I plus of S. I already told you that the chronological future of S is the union of the chronological future of all points in it. So that's it. And the boundary, therefore, is this sort of thing. Okay. So this is a codimension 1 acronal submanifold. This is going to be useful sometime in the future. So, I mean, the boundary of the chronological future typically is a null sort of thing. In the pictures we can draw, but it's actually a rigorous theorem, and this is proven in Wald's book. So, in the notes which I'll circulate, I can mail them to any of you. These either the proofs of many of these statements are there, or they are or there's a pointer to either Wald or Witten or Hawking or Gerosh, someone who's proved it. Okay. I could go through the sketch of the proof, but I think in view of time, I probably avoid it. Okay. And now we come to a very fascinating and confusing subject, which is the end point of a curve. So let me again tell you the intuition. So let's say I have a curve in a manifold. What would qualify to be called its end point? Okay. Of course, it should be what we think it is. It's just where the curve ends. But topologically, the definition is that these everys are very important. Every open neighborhood O of P, so completely contains the curve for all lambda greater than lambda 0, then some lambda 0. So let me illustrate that. So here's my curve, and every point on it is parameterized by my coordinate, parameter lambda, which could be affine, not necessary, but it could be, and usually is. And so let's say there's a point here called lambda 0, particular value of lambda, which tells me a particular point on this curve. Now, my P should be such that once I've crossed lambda 0 on this curve, all the remaining points of the curve are enclosed in every open set of P, no matter how, that contains P or around P, no matter how small. So intuitively, the curve sort of runs out of steam very, very close to P, and it may hit P, it may not hit P, but it's so close to P that that's where it's ending. Okay. Why did we have to resort to this gymnastics? Is because P doesn't actually, so this is P. P does not have to be on the curve. It has to be in the manifold M. So you can imagine very easily parameterizing a curve by a parameter lambda, which sort of slows down and reaches maybe some very large value like lambda equals infinity there. And that's where P is. And so the curve hits P only in the limiting sense when lambda is going to infinity, but there's no actual value of lambda where it's hitting P. So in that case, P is still an endpoint of the curve, even though it's not on the curve. Of course, it's much easier if P is on the curve, then it's an endpoint just if the curve ends there. But this definition is broad enough to include P's which are endpoints of the curve without actually being on the curve. If there's any confusion, please do ask. It's not very trivial.
Limiting point in that Euclidean topology.
You could say that, yes. You could say that. I won't disagree with that, yes.
Quick question.
Yeah, it's like a limit point in the Euclidean, yes, yes.
You said that every open neighborhood of P it contains the curve, but if I have
after some point, so contains the curve when lambda crosses some point on the curve.
I could have a neighborhood that only goes between P and 1 to 0.
Mm-hmm.
So the values of 1 to 0 until that open neighborhood are not contained in the neighborhood.
So you're saying that I have some lambda 0 and the curve doesn't go beyond it?
No, I'm saying so if you have a curve,
yes.
you have 1 to 0 here, and P here.
Yes.
I can draw a neighborhood around
yes.
P
yes.
such that these points,
these points don't, exactly.
But they're bigger than 1 to 0.
So then, okay, so if I have, okay, I should have said this for some lambda 0. And you can pick lambda 0 wherever you like, but there should be a lambda 0 such that after lambda 0, the curve is as close as you can imagine to that point. I think in all practical cases, the curve either physically ends at that point or it comes sort of very slowly to that point and never quite reaches there, but it's so, in the same, I don't know, in the same sense that, I don't know, tan inverse or something reaches pi by 2. It just comes very close to it and gets closer and closer. That's the idea. Good. And there are exercises in my notes which will tell you how to look at these. And now comes a very, very key definition. So we've defined an endpoint. And now we say a curve with an endpoint is called future extendable. And if it doesn't have an endpoint, it's future inextendable. What's the intuition behind this? Well, supposing I have a simple manifold M and I have a curve and it has an endpoint P. Okay, and I, who have decided what curve I want to draw, have drawn a curve and it ends at P. Now, I cannot make theorems about where this curve goes and what it crosses if I am allowed to stop the curve arbitrarily anywhere. I can't, for example, say that I have a surface in the future that all curves pass through, because I, as a human being, can be perverse and let my curves end somewhere. If they end, they're not going to pass through any point beyond. Okay. Now, we don't like those kind of curves. Those are the future extendable ones, because we can't make theorems like all curves pass through my surface. But if we restrict to future inextendable curves, then we can make theorems, which we will do in a moment, or definitions saying all future inextendable curves pass through a given surface. So I want to prevent people drawing curves like this, which just artificially come to an end for no good reason. Now the converse is when P is a point that's now deleted from the manifold, the usual mathematician's example. Now there isn't an end point because P isn't in the manifold. So the end point should be in the manifold. I've deleted the end point. Now if I draw a curve, I have every reason to say that this curve is future inextendable because there is no way I can get it beyond P without going through P. It's approaching P arbitrarily close and P is not in the manifold. So the curve has gone and ended there and it's over. It has no future. Okay, so when P is deleted, then the same curve is future inextendable. In fact, I can do something better. I can have a nice long curve and then delete one point, and I've split the curve into two inextendable curves. Both sides are inextendable. One is past inextendable, one is future inextendable. Okay. This is the terminology is a bit confusing because we are really saying if it ends at a point in the manifold, then it's extendable, and the implication is why don't you extend it? Why did you end it? It was your choice to end it. But if the point is deleted, then it's a curve that just ends there, and it's not my choice to not extend it. I just can't extend it. So then it's an intrinsic property. So extendability separates out those properties of a curve which tell us something about the manifold and those properties of a curve which only tell us about I who made that curve. So inextendable is the good kind. Extendable is the kind that's just artificially introduced, that's sort of not telling me anything about the system but just about the curve itself. So the behavior of inextendable curves is interesting. The behavior of extendable curves is not interesting because they're extendable. I hope that, I mean, these are very vague statements, but I hope it's clear what it means. Okay, good. Interesting theorem. Yes, I'm coming to them. Right now, I don't think I said anything about causal. Yeah, sorry. I did. And I should have. Very bad of me. Well, endpoint of a curve is, okay, yeah, exactly. I should have said causal and I should have said here, causal. Thank you. Causal curve, very important. Okay. In fact, here also, so let's see, right from the discussion of endpoint. So besides causal, I should have said future directed, but I think that's okay because, you know, this is true for future directed, it's also true for past directed in the reverse sense, you know, for lambda less than some lambda naught, it comes to an end. So future and past isn't that important to specify, but causal was very important. A lot of things are only true of causal curves. Good. Okay. Now, an interesting theorem, and it's not very simple to prove, but it relies on something I did earlier. Let x mu be a past inextendable, causal curve through P. So it's this, and here is P, and it's past inextendable. Okay, now let's write like this. Now I've said it's causal, that means it could be time-like or it could be null. It's not necessary that it be everywhere time-like. It could be fully null, or it could, I didn't say it's a geodesic, so it can be time-like in some segments, null in some segments. But the theorem says that there exists a time-like, a past inextendable, time-like curve in the causal future, in the chronological future of this curve. And through any point, through any P, any Q. I'll draw it and then it will become clear. Any Q in I plus of P. Sorry, I'll clarify the diagram in a second. Then we'll see what's happening. So here's a past inextendable causal curve that passes through P and then goes to the past inextendably. And the statement is that yes, the statement is that if there's a point Q over here, so this is in the chronological future of P, then I can always draw a past inextendable curve that's fully time-like through that Q. And so instead of considering this curve which could have null segments, I could consider another curve which is, so to say, above it and which is fully time-like. And this is only causal. The point is that this theorem guarantees that this constructed time-like curve will also be past inextendable. That's the non-trivial part of the theorem. Otherwise, it's easy to just do it. And what's the trick? The trick is that you draw a curve like this, which starts out well separated because Q is a different point that's been given to you. And then you make this curve come as close to this curve as possible as you go to the past. Okay, and then what you're ensuring is that if this had an endpoint, this would also have an endpoint. Since this doesn't have an endpoint, that can't have an endpoint, and that makes it past inextendable. Yes?
Could we also construct this curve by just going from Q to P, but then following the...
Not necessarily, because it might not, Q might, for example, okay, let's see, no, because if I went from Q to P and then came this way, then on the way here there might be null segments. You see, if this original curve has any null segments, then I have a problem. If it has no null segments, it's already time-like and I don't need this theorem. So I want to get rid of any null segments it might have, and I can start with another point Q in the chronological future and sort of shadow it from above, coming closer and closer in the past. The real trick is that the closer you come to this curve in the past, by doing that, you guarantee that whenever this has an endpoint, this must have an endpoint. Therefore, since this is inextendable, this must be inextendable. And there's a detailed proof of this in Wald's book. Good. This theorem may not be needed for much of what we do. It might come in somewhat later. And now we get to a very, very interesting concept, and I should say that in a way what I've been describing up to now was pre-1960s. This is now we are getting to mid-1960s when really causality, which we've discussed quite threadbare, turned into questions about dependence. And dependence has to do with events in physics influencing the future or past. And causality was not by itself enough to guarantee to what extent we can influence points in the future and the past, or be influenced by points in the past, and which points can influence us and which ones we can influence. And this is captured by the domain of dependence, which is quite different from the chronological or causal future of a point. So first of all, it's called D plus of S. So it's the domain of dependence of a set. The set can be any kind of set. It could be one point, or it could be a submanifold, or it could be anything. But S has to be acronal. So we are only going to talk about domains of dependence of acronal sets. In fact, in this case, we are going to also make it space-like. I told you earlier that an acronal set has to be locally space-like or null. Now we'll insist that it's space-like, but that's not enough. We have to say acronal as well to avoid that helix kind of space I showed you earlier. Okay, and so it's the set of all points such that all past inextendable causal paths through P pass through S. So let's draw it and it will become clear. Yes, it's the future domain of dependence, exactly. And of course, there will be a corresponding past domain of dependence by which will be called D minus of S. So here's S, and here's any point P. So S is given, and I have to test, is it I have to find out what is its domain of dependence. Okay, and S is given to be acronal and space-like. And now I take an arbitrary point P in the future of S. Okay. Now my statement is that any causal curve that I can draw from P can't be space-like. It has to be either null or time-like or combination of the two, must cross S. There's no causal curve that cleverly can go around S and miss it somehow. Okay, and this is this is a very central concept, so I'll spend as much time as you like on it. So it's the future domain of dependence of S is all points in the future, all points like P, such that all past directed inextendable curves intersect S, pass through S. And now you can see why past inextendable was important. Why did I spend all this time on endpoints? Because, well, supposing I construct a very nice S and I insist that its domain of dependence is a lot of points in the future and that P is in that domain, some wise person comes along and says, no, I'm drawing a past directed curve that ends here and it doesn't intersect S, so so this isn't P isn't in the domain of dependence. And that's why this is extendable. This is an extendable curve. That's why I need to only consider past inextendable curves. I'm not allowed to test the domain of dependence by allowing for past extendable curves, because this curve, since I refused to extend it, was never going to cut S, and I didn't learn anything about the manifold. I just learned that some foolish person drew a curve that ended here. However, if this point is not in the manifold, then we have some fun. If this is deleted, then there are curves which, roughly speaking, are here, which, coming to the past, end just short of this deleted point. So they are past inextendable, and therefore they don't cut S. And even if one such curve exists, then that point is not in the future domain of dependence.
So, no,
Yes.
you used the causal curve.
Causal curves, absolutely. I think I said that here. Past inextendable causal curve. All past extendable causal curves. Yeah, causal absolutely essential. Well, one obvious thing is that if it's not causal, it could be, first of all, even past inextendable doesn't make sense. But I mean, a non-causal, like a space-like curve, could start here and go around in circles forever, just not cut anything. And it's often, it just won't do anything. Yes.
Are you including even almost extendable paths? Are you including paths which go to infinity? Or
Absolutely. So, inextendable paths broadly are, there are really two kinds. Those which go to infinity and those which sort of run out where the manifold somehow ends or has some missing regions, one or the other. So then I generically draw them this way. If Q is deleted, then I do have this possibility, and then I have a problem with the future domain of dependence not being everything that I thought it might be. Now, there's a very fun consequence. So, this is a very beautiful paper I do want to reference by Gerosh, 1970, called Domain of Dependence, where he works this out. And one thing, this is just me, and I shouldn't say these things when it's being recorded, but unlike Hawking and Penrose and even Wald, who I think have some very sublime intuition and won't necessarily share it with you, Gerosh always gives you a bunch of examples for everything, and for me that's like very heartwarming. This example, this example, this example. In fact, I think this paper has like 6 examples or 7 that illustrate different aspects of domain of dependence, and it's a very short paper, but it's wonderful. So one of the consequences is interesting, that and that's almost obvious, to have any domain of dependence at all, S must be a codimension 1 hypersurface. So besides being acronal and space-like, it really has to be a codimension 1 hypersurface, because, well, what if it's not? Supposing S was a line, then there are plenty of past directed inextendable curves that just won't pass through that line. They just pass around it and go to time equals minus infinity without hitting it. So so therefore, in all such cases, if S is a point or a codimension 2 surface or anything like that, then S is its own domain of dependence. There's nothing outside S that's in its domain of dependence. Okay, so we've really set up things to have a codimension 1 hypersurface, and since it's going to be acronal, we are now almost at the point of the very key definition, which is the Cauchy hypersurface. So these ideas will allow us to define a particular kind of S called the Cauchy hypersurface, which will be the one on which we give initial data in order to do physics. Okay, now these domains of dependence, D plus and minus, need not be closed sets in general, and there are all kinds of theorems. I'll skip some of them and get to the key one, which is a definition actually. A Cauchy surface, or often called Cauchy hypersurface, in a manifold M is an acronal space-like surface sigma such that every past inextendable causal path through every inextendable causal curve, causal path through P in M passes through sigma. Another way of saying it is, it's a surface whose domain of dependence, d plus as well as d minus, is all of the manifold M. So I'll call it CHS, Cauchy hypersurface, d plus and minus of sigma, d plus of sigma, union d minus of sigma. You could also take the union with sigma itself, but sigma is in both d plus and d minus. So this is equal to M. So it's that hypersurface, if it exists, or it's actually a class of hypersurfaces, such that everything in all of M is in the domain of dependence of that surface. And it's an acronal surface, so you cannot go along the surface with time-like paths, and its future and past are domains are all of M. And now there's a kind of jackpot at the end of it. A manifold M with a Cauchy hypersurface is called globally hyperbolic. So if the manifold has a Cauchy hypersurface, then it's globally hyperbolic. Not all spacetime manifolds have a Cauchy hypersurface. Very easy to construct some that don't. One of them, of course, is our famous Minkowski with some point deleted. Then it just doesn't have any Cauchy hypersurface, because there'll always be some points in the manifold which, however, are not in the domain of dependence of your surface. Okay, you can move your surface up and down in time. Remember, it's a space-like surface. It is in fact a space-like surface. You can move it along time, and what you can do if you're clever is, well, supposing your manifold is missing a point. Supposing this is your manifold and this is your missing point, you might be able to get by saying this is my sigma, so its future domain of dependence is all in M, but its past domain of dependence has this awful deleted point, and so the whole union of d plus and d minus is not M. And if you try to put this in the past of P, this is the deleted point. Then you similarly have a problem, because now its future domain of dependence together with its past is not all of M. Okay, so but this isn't the only class of things that are not globally hyperbolic. There are plenty of good examples, better examples. I don't want to get into too much detail, but let's say about this ADS has this boundary, and so things past directed lines like this can go to the boundary. Now a lot will depend on your boundary conditions and so on, but if I try to draw my Cauchy hypersurface here with this being time, then there can be past directed lines, causal curves that just don't reach sigma. So ADS is not globally hyperbolic. Okay, so in fact, right, so there, so it's not absolute that you have to have everybody be globally hyperbolic, but it's a very sensible. Okay, the point with ADS though is that this only happens when things hit the boundary, and the boundary is nice. We sort of learn about this boundary. That's where some CFT lives. That's where there's some boundary conditions. So you can still define, you can have well-defined physics problems on ADS despite having a boundary, but you have to do something else. You can't just declare it to be globally hyperbolic and proceed from there. You have to talk about boundary conditions at the spatial boundary. On the other hand, if you're in asymptotically flat spaces which are reasonable, then this is your sigma, and if you decide your initial values of all fields on this, then they will propagate to the future domain of dependence. So signals will propagate to there, and so everything that you do here will influence the points there, and everything that anybody does over here will influence you somewhere on sigma. So it's like domain of dependence is like domain of influence. And globally hyperbolic is a very nice thing because it's intuitive, right? I mean, once you have a Cauchy surface, then a lot of good things happen. So I'm out of time now, but I'll just take 2 more minutes and give you a few statements about Cauchy hypersurfaces and globally hyperbolic manifolds, and then we'll pick up after lunch. So one question is sigma closed? Closed means contains its endpoints. So sigma is a Cauchy hypersurface. Does it have to be closed? So Wald requires it to be closed. So he says an acronal space like closed hypersurface. But in fact, Witten argues that it doesn't, you don't have to assume it because you can prove it. And okay. Beautiful quote from Wald, which I should read out. In a globally hyperbolic spacetime, the entire future and past history of the universe can be predicted or retrodicted from conditions at the instant of time represented by sigma. I don't think anyone could say it better. So here's sigma. Time goes this way. There's no rule that sigma has to be t equals 0 exactly in any coordinate system. You might fix your coordinate system, and this might be a bit curvy, but it should be space-like, it should be acronal, and its domain of dependence should be everything. Okay, and clearly it divides space-time. So a Cauchy hypersurface divides M into a future and a past. So in our minds, it is, we can just define our chord. Once we have a sigma, we can always say time is 0 on that, positive there and negative there. Okay. Now an interesting thing is that there cannot be closed time-like curves. First thing is that an inextendable path cannot intersect this Cauchy hypersurface more than once. So here's one property. Here's P, here's my inextendable path. There's no way it can do something like that. Why? Well, this obviously doesn't look time-like, but that's my diagram. Who knows, in some weird manifold if this whole thing might be time-like. Well, it might be, but let's focus on these 2 points and note that if the whole thing is time-like, then this is time-like. But it's a time-like curve joining 2 points on sigma. But sigma is acronal. It has no time-like curve joining any 2 points. So therefore, a curve can only intersect sigma exactly once. So any, I don't know, inextendable curve must intersect sigma, but exactly once. Once and only once. Also, there are no closed time-like curves. This is a widely considered to be a disaster for physics, because if the space-time was globally hyperbolic and you had a closed time-like curve, well, it's inextendable, it's closed, doesn't have an endpoint, so it must intersect sigma. But if it intersects sigma, then it intersects sigma repeatedly because it's closed, and that's exactly what we just said can't happen. So there are no closed time-like curves. So very good things happen in globally hyperbolic spacetimes. And yes, as I said, 1 point deleted in the future makes the thing non-globally hyperbolic. Let me show you one last very cute example due to Garrosh of a nice spacetime, in fact Minkowski, where you can define a hypersurface that looks nice but it's not Cauchy. So this is not Cauchy. You can see that it's acronal, it's a hyperboloid, it's perfectly acronal, it's in fact everywhere space-like, it's all good. But if I was here, I could come down like this time-like, and then I could bend like this, remaining always time-like. I'm just a little bit off the light cone, and I could be in extendable and go to minus infinity without ever hitting this hyperboloid. So this is not a Cauchy surface. Okay. Now you could ask, what is its domain of dependence? Well, the past domain of dependence is everything, because any future directed inextendable causal curve will have to hit it. But if you look at past directed causal curves, only those in this shaded region below the light cone and above the hyperboloid, these are in d plus of sigma. And anything outside this light cone is not in the future domain of dependence of sigma. And now, of course, we have one obvious statement that if I take sigma, because I like it, and I just take d plus of sigma and d minus of sigma and take the union, then I have a globally hyperbolic manifold for which sigma is a Cauchy surface. But that manifold is just this past of this light cone. That manifold by itself has a Cauchy surface sigma. Of course, the whole manifold also had a Cauchy surface, but not this one. So given a acronal surface, I can manufacture a manifold for which it is a Cauchy surface, but that may not be all of my M. Okay, I'll stop here, sorry. We'll resume whenever. Yeah, thank you.